calm, intriguing, slightly suspenseful. The planet Jupiter is not what you think. Almost everyone is wrong about Jupiter because almost everything you were taught in school about this planet is wrong. This is not a giant ball of gas. Jupiter is a liquid planet. And as if that wasn't strange enough, it's actually a liquid metal planet. Beneath those iconic clouds lies one of the deepest mysteries of our solar system. So let's dive in. This is the first close-up photograph of Jupiter ever taken. It was captured by a NASA spacecraft called Pioneer 11 in the year 1974. And this is the first moving picture of Jupiter. It's a time-lapse of images captured by Voyager 1 as it approached in 1979. Now, the problem with these observations is that beyond looking really cool, they don't provide any answers about the true nature of the gas giant. They only raise more questions like, what is this thing made of, and how did it get so big? The actual size of Jupiter is very difficult to comprehend. Not only is it really big, but it is heavier than the weight of every other planet in the solar system combined. It takes up enough space to fit 1,000 Earths inside. For a more relatable sense of scale here, if the planet Earth was the size of a grape, then Jupiter would be a basketball. Now, our general theory for how the solar system came to be starts with a big disk of rock and metal and gas and dust and stuff, all spinning around the newly formed sun. And then over millions of years, all of the stuff in that disk keeps smashing together and forming into bigger chunks of stuff. And then as those chunks get even bigger, gravity starts to kick in and attract even more stuff. So under that theory, Jupiter would have formed when one of those chunks got so big that its gravity started capturing massive amounts of gas that were swirling around inside the disk and just kept doing that for billions of years until it became what we see today. That makes sense, and if true, would mean that inside Jupiter there must be a very big and incredibly dense core of solid rock and metal. An alternative theory, just for fun, is that Jupiter actually started its life as a separate gigantic cloud of gas that was sitting just outside of the early solar system. Over time, that cloud got so big that it eventually collapsed under its own gravity and formed into a dense ball of gas. This is pretty much the same way that a star is formed, only stars need a much bigger cloud of gas to get started. So in this case, you just get a really big planet, and then eventually that new planet got pulled in by the gravity of the sun and settled down into an orbit. If this were true, then Jupiter wouldn't really have a core at all. It would just be like a big layer cake of gas. But the theory most of us were taught was about the big solid core that captured all of the gas. And again, that does make sense. It's not a crazy thing to believe, but it's also not correct. Our first real breakthrough with understanding Jupiter came in the mid-1990s, and this is one of those insane coincidences that sounds too good to be true. But in July 1995, the planet was hit by a comet. This is not a common thing. It's estimated that a collision like this might happen once every 6,000 years, but we were around to see this one, and we had the technology to watch it all happen. This comet was named Shoemaker-Levy 9, and it was a very big chunk of frozen ice and rock hurtling through the solar system at 216,000 kilometers per hour. It's hard to say how big the comet really was, because by the time we found it, the powerful gravity of Jupiter had already fractured the object into a couple dozen pieces. But the largest of those pieces was still around 2 kilometers across. And at this point in time, NASA had their newly operational Hubble telescope ready to observe the impact. But there was a big problem. The pieces of the comet were going to hit Jupiter on its far side, out of view from the Earth. We were going to miss it. Except, at the exact same time that this once-in-6,000-year event was happening, NASA just also happened to have a spacecraft arriving at Jupiter. This is Galileo, named after the first astronomer to have studied the planet through a telescope. The probe was launched in 1989 on a mission to investigate Jupiter and its moons. It was scheduled to arrive in December 1995, and now it had a clear view on its approach of the comet impact. What it saw was 21 separate collisions over the course of 6 days, with the largest chunk of comet unleashing the equivalent energy of 300 million atomic bombs, making it the biggest explosion ever caught on camera. As the planet rotated around, the Hubble telescope was able to see the aftermath of those strikes. They actually left behind these big black holes in the clouds, and they kicked up massive plumes of debris that were thousands of kilometers high and lingered above Jupiter for months. And this is what the Galileo spacecraft arrives at. The insides of Jupiter have been kicked out into space, and the probe is able to fly right through them. This is our first look at what's underneath the cloud layer that people have been staring at in wonder for hundreds of years. The most interesting thing that Galileo found was actually water, a lot of water, and scientists thought that was pretty weird. Weird enough that they started working on another mission to Jupiter with a new probe that would be designed specifically to seek out the planet's true nature. That mission was named Juno. The spacecraft was launched in 2011, and it arrived in 2016 to begin solving the mystery within Jupiter's core. So when we say that everything you were taught in school is wrong, that's because we didn't even start to learn the real truth until this past decade. So here's what your science teacher didn't know at the time. Jupiter is not made of gas. It is covered in big, thick clouds of gas that form all of those swirling rings and storms. But those clouds are just a thin layer on top of much stranger things down below. But let's start from the top. In the clouds of Jupiter, the temperature is below -100 degrees Celsius. Water ice crystals interact with ammonia, which acts as a natural antifreeze, allowing liquid water to exist in the upper cloud layer. As droplets collide with ice crystals, the clouds become electrified and trigger gigantic lightning storms that rage all across the surface. This super-chilled water and ammonia mixture eventually clings together into slushy hailstones that fall down into the lower atmosphere, where they melt into rain, evaporate, and then rise back up to start the process all over again. These jets of hot gas that rise up to fuel the raging storms on the surface reach deep down into the atmosphere of Jupiter. This is what we are seeing in the Great Red Spot. Not only is it thousands of kilometers in diameter, it also extends down hundreds of kilometers into the ammonia rain. The red spot reaches up higher than any other clouds on Jupiter, extending above the surface level and absorbing more UV light from the sun, which then reacts with chemical compounds in the storm and creates that deep red color. Imagine a cloud 10 times taller than Mount Everest and 10 times deeper than the ocean, and that still wouldn't even be big enough to capture the scale of the red spot. As spectacular as this outer layer might appear, the average depth of these ammonia and water clouds is only around 50 kilometers. As we descend down below the clouds and into the lower atmosphere of Jupiter, the temperature begins to rise. This heat is caused by pressure. When you compress molecules, you concentrate their energy, and the pressure is created by gravity. The incredible mass of the planet itself is pulling all of this material down and squeezing it tighter and tighter until some really weird stuff begins to happen. The further down we go into Jupiter's gravity well, the heat and pressure build up. It's like traveling through a fog that becomes thicker and thicker until eventually it becomes a liquid. Except here, the fog isn't water, it's hydrogen. Hydrogen is the lightest element in the universe, and in an extreme gravity environment like the inside of Jupiter, it's the only thing that can stay afloat. All of the heavier elements have already been pulled down into the planet's core. At a depth of around 1,000 kilometers below the cloud layer, the hydrogen gas completes its transition into a liquid. And this is the closest we get to anything that might resemble the surface of Jupiter, an ocean of liquid hydrogen, the largest ocean in the solar system. So while the giant planet might be covered by a thin shell of gas, it's definitely not made of gas. It is a liquid planet. But this is a far stranger liquid than anything we've seen before. On Earth, we can liquefy hydrogen by making it very cold. The atmospheric pressure of Earth lowers the boiling point of hydrogen to around -250 degrees. But on Jupiter, the opposite effect is going on. The intense pressure raises the boiling point so high that it can exist as a liquid, even at temperatures well over 1,000 degrees. This ocean is about 20,000 kilometers deep, 2,000 times deeper than Earth's ocean. And as we reach the bottom of everything, the pressure and temperature created by the gravity well have a very bizarre effect. Under millions of times the pressure of Earth's surface, at 10,000 degrees Celsius, hydrogen changes state into something called metallic hydrogen. Now that doesn't mean it turns solid like steel.
It's still liquid, but a metallic liquid, maybe something like the mercury inside a thermometer. The biggest change that takes place here is that metallic hydrogen now has the ability to conduct electricity. Jupiter's gravity squeezes so tightly down here that electrons break free from the hydrogen atoms and flow throughout the liquid, generating an electric current. This liquid metallic hydrogen makes up the majority of the planet's interior. It's about 40,000 kilometers deep, and down at the bottom of everything lies the solid core of Jupiter. Kind of. We previously believed there was a compact, dense object in the middle of Jupiter, about the size of the Earth, and made up mostly of iron and rock. That made sense, but new research is uncovering that the planet's core is much more fuzzy, as in, the transition between liquid metal and solid core isn't a hard line, meaning the two layers kind of mix together. The fuzzy core spans about half of the planet's